Hello, good morning, everyone. If you can hear my voice, can you say hello, sir? Okay, very good. Can see your responses. Good morning, everyone. I am ND Ojo, and I'll be taking you another part of CHM 101. My colleague last week has already introduced you to another aspect of CHM 101. So today we'll be looking at another concept that we call acids. Actually, I'll be taking you acids, bases, salts, and buffer solution. But for the sake of this particular contact here, we'll be focusing more on acids we have in our environment. Well, I want to believe that you've been familiar with the concept of acid right from your secondary school days. Okay, before I move on, Some some of you who may not be able to join right now can also be following us on YouTube. The class is available right now on YouTube. So you can follow us on YouTube. And if for any reason the network signs you out, you can also follow us on YouTube. The link to the YouTube is already available on the LMS. You can just click it and then you'll be able to follow us. So just like what I was saying, okay, let me share my screen with you. Let me share my screen with you. Okay, a minute. All right. Well, let me hope that you're able to see my screen here. Let's hope you can see my screen. If you can see my screen, can you just make a comment? I can see it. Okay. Yeah, thank you. So now I'm sure that you can see the screen. All right. So I may not be following more on the chat section, but let's see how far we'll be able to go. Okay, let's see how far we'll be able to go. Now, from your secondary school days, you were told that an acid is a substance that when you put it in solution or maybe in water, you dissolve it somewhere, then it should be able to release hydrogen ion in solution. Remember, I'm calling it ion, not ion. So it releases hydrogen ion in solution. So under this course, under this particular section, basically, we'll be looking at acid, basis, pH, salt, buffer solution, just like what I said earlier. So that's just the broad division, and this is the content of the course. And at the end of my own part, this is what I'm expecting you to be able to do. You should be able to define what acids are, what are bases, what do we call salt, do we have different types of that? You should be able to list the properties of acids, bases, and also some properties of salt. You should be able to list them. And we'll also be looking at how we can calculate the pH of strong acid, the pH of weak acid, strong base, weak base. And can we even calculate the pH of a buffer solution? What is a buffer solution? What does it mean? What do we use this for? What are the applications? And how can we, using calculation method, determine the pH of a buffer solution? Okay, so we'll be looking at that also. And you should be able to differentiate between acids and bases. What is an acid? What is a base? You can use the definitions and properties to differentiate them. Then what do we mean by neutralization? Is it an acid coming together with a base or something? Is a part being used up by the other? So we will look at that, but not in this class, but that is just the general learning outcome. Specifically under this unit, which is unit 1, we'll be looking at acids and bases in our environment. And today's class will be focusing more on acids. So we should be able to define what acids are, list at least 3 properties of acid, and if we're able to get there, we can also calculate maybe the pH of a strong or a weak acid. So now we have acids in our environment. Do you know that acids are just all around you? Possibly you have even come in contact with an acid today. Maybe you have even touched an acid, or you have taken something that contains an acid today. We don't know. We are not very sure. The day is still very young. But just believe that acids are all around us. So when you hear the word acid, sometimes we feel scared. It sounds like something corrosive, dangerous, something that can burn, something that can consume, that can burn leather, burn skin, and all that. Yes, you may not be incorrect. You may not be incorrect. However, with all this that we know, or that we have heard about acids, we still have acids or acidic solutions all around us. Some of them are in those things we interact with, even at home, maybe in the kitchen, those unripe fruits we have, they contain acids. And different kinds of them contain different acids. We have citric acid, we have ascorbic acid, and all that. They mostly are, we can get them from fruits. And sometimes when you have milk, especially those steam milk, you just puncture it, you take a part of it, you leave the rest, maybe covered or uncovered. After 2, 3, 4 days, when you get back there and you taste it, the taste will not be the same again. So what has happened to the milk? As a particular sugar there be converted to an acid, what has happened inside that milk? That is another example of having an acid formed even very close by in your environment, something that you see, something that you can also experiment at home. But we are not advising you to drink or to taste an acid or maybe sour milk. It may not be so good for your health. Then some of these medicine we also take, like aspirin, they contain acid, like salicylic acid and all that. So some of them also contain acid. That's why sometimes when you want to take them, they will advise you, ensure you eat something before you take it, or maybe ensure you have taken some water and all that before you take the medicine. Just follow medical advice anytime you want to use a medicine, and don't prescribe medicine for yourself. Ensure that you consult medical practitioners. Well, this other part, I want to believe or maybe assume that you know that we have acid in our stomach. Now I'm giving you this exercise to do. What is the name of that acid that is present in our stomach? Every human being, every normal human being, what is the name of that acid? You can just type it in the chat section. Just type it in the chat section. Let's see. What's the name of that acid in our environment? Okay, I can see some of you writing gastric acid, hydrochloric acid, gastric HCl, dilute HCl, conc HCl. Well, conc, dilute, whichever. Okay. All right, all right, all right. Yes, you have all done very well. Yeah, you have all done very well. Someone typed renin and all that. Well, is renin an enzyme or is it an acid? You may also need to check it out very well. You may need to check it out very well. So find out very well. The acid, yes, you're correct. But we have hydrochloric acid in our stomach. And now I'm giving you another exercise to do. Now look at hydrochloric acid. That's all. HCl. We also have hydrogen chloride. Hydrogen chloride and hydrochloric acid, are they the same thing or are they different? If you know the difference, just type it there in the chat section. Just type it there. Hydrogen chloride or hydrochloric acid, are they the same? If they're the same, say they are the same. If they're not the same, say they are not the same. and put the reason there why you think they are not the same. If you say they are the same, put the reason there why you think they are the same. Okay, I can see some of your responses there. That's fine. That's very fine. So hydrochloric acid is present in our stomach, and it is actually really helping us. It helps in digestion and all that, helps to break down. It helps to break down some of the food that we take. Sorry in case if my network is not stable. It may be maybe some phone calls that are coming in when I'm still having this class. Hello, everyone. Can you still hear me? Okay, okay. Thank you. Some phone calls are actually, some phone calls are disturbing my network. Okay. Thank you. I can see your responses. I can see your responses. Yeah, thank you. Okay. So, like I was saying, we have acids all around us in our stomach. And also, this is rainy season. This is rainy season. Sometimes the rain falls, and then we, majorly from this part of the world, believe that rainwater is one of the purest water we have available. So we just take it, we fetch it, we drink it, we think it's potable and all that. But do you know that we can also have acid rain? You can have a case in which the rainwater, when you check the pH, the pH is just not what you think it should be. The pH, when you check it, well, when you check the pH may be greater or maybe may even be less than what we're expecting. If it is less than what we're expecting, then it can be an acid solution. So maybe one of these days when you are fetching the rainwater, when you're fetching the rainwater, you can, if you have a litmus paper, you can just use it to test the rainwater and see whether it is actually neutral or whether something has contaminated it. Maybe we have some pollutants, some dissolved gases, or some dissolved acidic gases in heat. Examples of such dissolved acid can be SO2, CO2, NO2, and all that. They can be present in the rainwater. So it may not be exactly of pH 7. The pH may not be what we expect it to be. All right. So far we have looked at some acids in our environment. We have mentioned unripe fruit, salmic, aspirin. That's an example of a medicine, car batteries, then the one in our stomach, and the acid rain. Do you think we have left one or two acids out in our environment? If you think so, type it in the chat section. That's okay, what about this acid? What about that other acid? Type it in the chat section. Okay. Yes, I can see some of your responses. That's fine. All right, as you're typing that, let's look at physical properties of an acid. Physical properties of an acid. One of the physical properties of an acid is it has sour taste. It has sour taste. Sour taste, we have already said previously, if you have milk, you puncture it, you leave it there, dissolved in water for some days, you taste it again, it's no longer fresh. So that is the sour taste. That's an example of the sour taste we are referring to. This does not mean that when you enter into the lab or they label something acid, you should put your tongue there. That can be very dangerous. In the laboratory, do not taste anything, even if it looks like water. Even if it looks colorless, transparent, whatever you call it, whatever it looks like, if it is labeled or not labeled, do not put your tongue on your mouth on any chemical or any liquid or solution in the laboratory. That can be very, very, very dangerous. So acids have sour taste. So if we don't want to taste acid, then who tasted it to know that it has sour taste? Well, the good example is that of the one we have in milk, in sour milk. Someone, maybe even you, have tasted that milk, that sour milk, and they tested it and they saw that there was the presence of an acid there, maybe lactic acid or so. So that gives us an idea that acids they can have sour taste. They can have sour taste. Well, are you all still following? Can you still all hear me clearly? Okay, let's see. Can you still all hear me? Trying to see. Yes, okay, that's good. That's good. That's good. All right, so we have talked about the sour taste an acid may have. Then we also have what we call concentrated acids. But whether it is dilute or it is concentrated, you may not even know. So don't play with any acid around. Okay, now let's take it as a concentrated acid. Concentrated acids can burn as if fire is burning wood or as if fire is burning leather. So we don't play with them. We don't joke with acids. Concentrated acids are very destructive. They are dangerous. They are corrosive. They can burn like fire. So we don't play with them. We don't play with them. And they can also turn moist blue litmus paper red. Now, if you moisten a blue litmus paper, that is, you just put it in maybe distilled water or water with pH 7, and then you use it to test whether an acid gas or you use it to test an acidic solution. If that solution turns the litmus paper, that blue, to red, then we can say that that solution is acidic. And the pH of such solution should be less than 7. So the pH of an acid solution is usually less than 7. And, well, most of the acids that we have, they are soluble in water. Let me say this concerning some of you typing in the chat section. Please just note what you are typing there. Just note what you are typing there, because this chat section is saved, automatically saved. So when we go there and we'll see your name there, maybe this note or something, and then you are typing something that's not supposed to be there over there, then just note that we are taking record of all that. Okay? So type just what you know can easily represent you. And what can represent your intellect, your good behavior, your good character. Type those things in the chat section. So let's move on. We said acids, especially these ones we've been defining before in our secondary school days, they can dissolve in water to give hydrogen ion as a solid positive ion. So that one is soluble in water. And it can also be a very good electrolyte. So that is why the moment we have an acid solution, we don't use it to joke with electricity, because it can easily conduct electric current. Okay? Yes, now let's look at chemical properties of acids. One of the chemical properties of an acid is that it can release hydrogen gas when it is reacted with highly positive metal. Highly positive metal, sodium, potassium, calcium, and all that. If you react such with an acid, then we can have evolution of hydrogen gas. And this reaction is one thing we should be very careful of. Do not try this under home condition, because the release of hydrogen gas, if care is not taken, it may lead to explosion. So be careful when you're carrying out an experiment. Dr. Joe has already told you, acid, when you react it with some metals, and then you have the metal atom, can liberate hydrogen gas. And then you want to get hydrogen gas, and want to do that under mommy and daddy's house, don't try it. Or you are in your hostel, then you just sneak out some acid from the lab, and then you want to try that at home, don't do that. That can be very, 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 very dangerous. So don't try that. Okay. So everything you want to do, you should do it under laboratory condition and ensure that it is the practical that has been organized, that has been well laid out, the instructions, the procedure, the precautions are all explained under the guidance of maybe a technologist or a lecturer. So don't do practical that is not, that they didn't give you to do in the laboratory. All right, let's move on. We said acids can form salt when you react it with an alkali. An alkali is another way of saying a base, especially for soluble bases. We call them alkali. And that is a neutralization. That's a neutralization reaction. That's a neutralization reaction. Now, under this part, can you give me an example of an acid and give me an example of an alkali and tell me what possible salts or what possible products we can have from there? Give me an example of an acid. Give me an example of a soluble base. That's like an alkali. And tell me an example of the product. You can put it in the chat section. Can you just type that very fast? All right, that's good. Ajawuhi. People. Acid, HCl. Okay, Abigail, I can see your equation. That's good. That's good. So be later on, you can consider changing the oxygen and the hydrogen to uppercase. Okay. Yeah. Yes, I can see your example. So we can have sodium chloride formed using that type of expression. You can have sodium chloride formed. Okay. I have many of you who have typed correct things in the chat section. Well done. You've done very well. Well done. Okay. Yes, so just like what you typed in the chat section, we have that kind of neutralization reaction in which a base reacts with an acid and that forms salt and water. We have that kind of expression. Okay. Then let's look at another thing. Do you know that you can prepare ammonia gas by the reaction? Okay, we can prepare an ammonia gas. Okay, we are not looking at this ammonia gas right now. I will tell you more about the ammonia gas in subsequent classes. I will tell you more about the ammonia gas. But let's take this step further. So we can have neutralization reaction. We can have the reaction with highly electropositive metal to give us hydrogen gas and then some other products. So we have been talking about what acids can do. That is their properties, the physical properties and the chemical properties. But how do we define an acid? Remember in secondary school you said, or maybe your teacher told you that an acid is a substance which when dissolved in water gives hydrogen ion and has a only positive ion. That definition I was giving to you was postulated by Arrhenius. So we call it the Arrhenius theory of acids. That is, acids produce hydrogen ions or hydronium ions in aqueous solution. So look at this type of example. We have, okay, let's say we are using Ha to represent an acid. This H is the hydrogen ion. The A is like the anion connected to it. Like we have H plus Cl minus. The chloride ion is the anion. The hydrogen ion, that is the positive ion. So you can have HCl as an example of Ha type of acid. So if you have Ha, this A can be any anion like SO42 minus, Br minus, NO3 minus, those are anions. So we have Ha dissolves in water and it gives hydronium ion or hydroxonium ion H3O plus, and then we have the anion released into solution. That's in aqueous form. So this is a general way of defining an acid according to Arrhenius. This is a very simple definition of an acid, and let me believe that you are familiar with this definition. All right, let's move further. Let's take a step further. So that is Arrhenius' definition, but we also have what we call the Bronsted-Lowry acids and bases. Bronsted-Lowry acids and bases. But we will be focusing more on Bronsted-Lowry acid. But in the case of Bronsted-Lowry, you can easily define the acid without also making a reference to the base. According to Bronsted-Lowry, they said an acid is a proton donor. So if a particular species, if someone is donating proton, there should be a recipient, someone or something that is receiving that proton. If there's no recipient, there cannot be a donor. If there's no recipient, we can't have a donor. So if you want to cage this type of process, then you can take the recipient away, then we don't have any donor. So in this case, an acid is the proton donor. And if it wants to donate proton, it means it has that proton to donate. Okay? In the next couple of minutes, let's say like 2 minutes, I want to show you a video. And this video should be able to explain to you more about the definitions of an acid. So just give me a moment. Just give me a moment. And for Precious, who needs the link to the LMS, that is just lms.ui.edu.ng, the normal LMS that we use at the University of Ibadan. Okay. All right, let's see this video in the next couple of minutes.
Thanks for stopping by. This is 2 Minute Classroom, and today we're going a little deeper into acids and bases.
Okay, can you see what I'm sharing here right now on acids and base definition? Can you see it? If you can see it, can you just type something in the chat section? All right, very good, very good. Yeah, okay, thank you. So let me enlarge it so that you can see it very well.
By looking at 3 different definitions: Arrhenius, Bronsted-Lowry, and Lewis. The Arrhenius definition is probably the most familiar to you. An Arrhenius acid is a molecule that will donate a hydrogen ion or a proton when dissolved in water. We call it a proton because a typical hydrogen atom has only 1 proton and 1 electron. So if you make it a cation by removing the electron, all you have is a proton. An Arrhenius base is a molecule that will produce a hydroxide ion when dissolved in water. So the acid provides a proton and the base provides a hydroxide. However, this is only when dissolved in water, and that's where the other definitions come in. With the Bronsted-Lowry definition, we only refer to what happens to the hydrogen ion or proton. So the acid is a proton donor, much like an Arrhenius acid, but the base is defined as a proton acceptor. So if there's a compound that will bond a free proton, it is a Bronsted-Lowry base. And unlike Arrhenius acids and bases, this doesn't have to be in water. The Lewis definition of acids and bases dives into organic chemistry, looking at the electrons of each atom. So a Lewis acid is a molecule that will accept a pair of electrons, while a Lewis base is a molecule that donates a pair of electrons. It's important to note that these definitions are just different ways to look at and understand acids and bases. Just because a compound can be defined as an Arrhenius acid, for example, doesn't mean it can't also be defined as a Bronsted-Lowry or Lewis acid. I hope this video helped you understand these different definitions a little better. If you want to know more about the properties of acids and bases, you can watch my acids and bases video.
Okay, you're welcome back. You're welcome back. I hope you have gained 1 or 2 things from that video. Okay, the video is too fast. Okay, maybe I will put the link to the video on the LMS so that you can watch and rewatch again. You can watch it and then rewatch it again. Don't worry, I will put the link there for you on the LMS. All right, now since we have We have looked at definition of acids. Okay, let me accommodate a couple of questions before we move on. Let me accommodate a couple of questions. If you have a question so far, you can raise your hand, then let's accommodate. Let's accommodate the questions. Okay, I'm coming. Stop sharing. All right, who am I seeing there? Olajumoke. Okay, let me see Olajumo. Oh, what are those raising hands? Okay, Olajumoke. Okay, Olajumoke Haribi Salah. What's your question? Olajumoke, are you there? Okay, maybe Olajumoke is not there. Let's go for so many hands up. Let's go for Esther. Esther. Is it Esther I'm clicking right now? Adegboyega. Okay, if I've asked you to unmute, then you can unmute and ask your question.
Good morning, sir.
Good morning, Adegboyega. Is it Adegboyega or Esther?
My name is Joy.
Joy. Okay. Good morning, Joy.
Yes, sir. Please, sir, in the video, they said that a typical hydrogen ion has a proton and an electron.
Okay.
Does that not mean that it will not have any charge?
A typical, come again.
Hydrogen ion. A typical hydrogen ion. Or be ion.
Okay. Are you listening, Joy?
Yes, sir.
Okay. Okay. A typical, just call it hydrogen.
Okay.
Typical
Okay,
hydrogen, yes. That one has an electron and it also has a proton in the nucleus. But the moment it becomes an ion, see, I'm not calling it a ion now. The moment it becomes an ion, then it means it has lost that electron. So it becomes H plus. Because when you lose a negatively charged particle, you become more positive. So the hydrogen ion becomes positive. It's no longer neutral. It's no longer a neutral atom. And it has lost the single electron it has. So it doesn't have any electron again. Okay. Is it clear now? Listen.
Yes, sir. Thank you, sir.
All right. You can mute yourself back and then put your hands down. Okay. Uni. Am I seeing Uni's? Okay, let me ask. Uni, are you there? Okay, maybe it's not there. Okay, let's ask Taiwo Adeniji. Taiwo Adeniji, are you there? No, I don't think so. Michael, who is there now? Is it Michael? Okay, Comfort. Whoever sees the notification to unmute, you can unmute. And then you can ask your question.
Good morning, sir.
Okay, good morning. Who is that?
It's Comfort, sir.
Okay, Comfort. Okay.
Yes, sir. You were mentioning aeon and ion. Which one? Like, can you tell us the difference between the aeon and ion?
The correct pronunciation is ion, not aeon. It's just in the pronunciation. The correct pronunciation is ion. It's not aeon. Okay, is it clear now? All right. Okay, let's ask another person. Okay, I may not be able to pronounce your name very well. Ezoge. Is it Ezoge? I may not be able to pronounce. Okay, good morning. Yes, good morning.
A question concerning the definition of an acid.
Okay, what's your name?
Ejizoje.
Okay.
if we are told to define an acid, do we give a hybrid definition or just say using Arrhenius theory to be specific, or how do we go about it?
Yes, you can be specific in your definition. When you define an acid, or maybe a base, whichever you want to define, say according to maybe Arrhenius, or according to maybe Bronsted-Lowry theory. So be specific about it, which particular concept you are using to define the acid. Just be specific. Okay. But if the question categorically states that define an acid according to Arrhenius, then you know the answer you will provide. Is it clear now? Okay. Ibukun Oluwa, I don't know if you're still there.
Good morning, sir.
Yeah, good morning.
Sir, I have a question. You said that all acids can conduct electricity, right? So I want to ask if in electrolysis we know there are strong electrolytes which are strong acids and weak electrolytes which cannot conduct electricity, and they are weak acids. So I don't think I'm still confused about that conducting electricity part.
Okay. Okay. Yes. All right. You may meet yourself back. So considering the concept of conductivity, especially electric conductivity for acids specifically, you may also need to consider through which means or through which mechanism is that acid conducting. Is it through mobile ions or is it through mobile electrons? If you want to look at mobile ions, then the ions there should be free to move. So, and if the ions should be free to move, possibly you have dissolved that acid in water. If that acid cannot go into water, then you can't think about conductivity using mobile ions. Also, even if that acid goes into water, what percentage of the ions are released in solution? What is the degree? To what extent does that acid break down or maybe break up in the solution? That can inform the conductivity, whether it will be a good conductor or it will be a poor conductor. And that is when the concept of strong acid and weak acid comes in. We will look at that in subsequent classes. The concept of strong acid, or weak acid, strong base, weak base, and all that. But just remember, if you want to talk about conductivity using mobile ions, then that acid should be in solution. If it cannot go into solution, then you can't talk about conductivity using mobile ions. So if we are referring to acids that can conduct, then that particular definition we're using and using solution as an example, we will be looking more at Arrhenius' theory of an acid. Yes, we may be looking more towards the Arrhenius theory of an acid. Don't worry, when we get to Lewis' theory, you will also see the dynamics, the different variations we can have as to how we can define an acid. Okay, maybe I have been able to answer part of your question, possibly. And the other one is about conductivity using mobile electrons. The conductivity using mobile electrons, that indicates that the electrons in that acid should be free to move. And that is easy to do when that acid, or maybe when that substance is a molten state. So if it's not a molten state and the electrons are not very free to move, then that cannot be called a conductor of electricity, whether poor or strong, good or bad. Then we cannot refer to it as a conductor. All right, thank you. Okay, let me just take a couple of questions more. Then we'll look at the assignment we have for today. And then we call it a day. Okay, Samuel Precious.
Good morning, sir.
Good morning.
Sir, please, I want to ask whether if you can help us to upload the notes on LMS portal.
Okay, I'll upload the notes on the LMS portal.
All right, thank you, sir.
All right, you're welcome. Okay. Oh, okay. Let's look at Lee. Is it Lee Shan? I may not be able to pronounce this name correctly. Are you there? If you've been
Yes,
hacked to.
sir. Yes, sir. Good
Okay.
morning, sir.
Okay. Good morning.
Okay. I wanted to lower my hand and I just answered that question about the notes. And sir, please also the other woman's note. I checked the LMS and it wasn't there. So I don't know, maybe you can contact her for her notes as well.
Oh, okay. Well, she is the other lecturer. Her name is Dr. Olatunde. The lecture notes will soon
Sorry,
be.
sir.
Yes. Okay. So the lecture notes will soon be on the LMS in the next couple of, say, minutes or hours. Today, possibly. She'll be able to see the note on the LMS. She is also here with
Okay,
us in the.
thank you.
Okay. Okay, John Praise, let's take your question. John Praise, are you there?
Morning, sir.
Yes, good morning.
Please, sir, my question is concerning the acid.
Okay.
The man said the laws, the Bronsted-Lowry law and the Lewis law. He said that a proton is a acid is a proton acceptor, while a base is a proton donor. For
Okay,
the
maybe you need to
Bronsted-Lowry,
watch the video again because
like I'm not clear with the laws. The laws are a bit confusing, like they are intertwined. I don't understand them.
okay, don't worry, I will explain it to you. You can meet yourself back. Okay, now let me share the screen again so that you can see it very well. Okay. Can you, well, I don't know, can you see the screen? Can you see the screen? All right, good. That's very good. Okay, now let's go over it again. Look at how we define a Bronsted-Lowry acid. A Bronsted-Lowry acid, it's a proton donor. A Bronsted-Lowry acid is a proton donor. Now look at Arrhenius acid. Okay, where is it now? See, Arrhenius acid is the one that produces hydrogen ion in solution. So, Arrhenius acid is constrained to solution. There must be solution there before you can define the Arrhenius acid. But for Bronsted-Lowry, you don't need a solution. The acid may be in solution, may not be in solution. But so far it can release a proton, then it is an acid. Now, so that you will not get confused, just take it this way. According to Arrhenius, an acid donates hydrogen ion in solution. So that is donate. Mind the word donate. According to Bronsted-Lowry, an acid donates a proton in solution. So Arrhenius calls it hydrogen ion. Bronsted-Lowry calls it proton. But the concept of donation still remains the same. So an Arrhenius acid donates hydrogen ion in solution when it dissolves in solution. A Bronsted-Lowry acid donates proton in solution. Is it clear now? Okay. Or you can look at this example in which we have ammonia and okay, let me make this bigger than this. Okay, now look at it. We have ammonia here. That's NH3 gas. It's a gas. It's just in the gas phase. No solution, no water, nothing. And we have HCl. We have HCl, which is hydrogen chloride gas. Initially I was asking what's the difference between hydrogen chloride and then hydrochloric acid. This one is in the gas phase. So we call it hydrogen chloride gas. This hydrogen chloride gas is not in solution, it's just gas. But even in the gas phase, it can release this hydrogen it has to this NH3. And then the NH3 becomes NH4+. The hydrogen it releases is in form of a proton, that is, the hydrogen that has lost its electron. And using a kind of coordinate covalent bonding, we can have the hydrogen ion, which doesn't have any electron, by the way, bonding itself to the nitrogen part of ammonia. And then we have the chloride ion, the Cl-. This is another example of acid-base reaction, and a salt is formed. The salt that is formed is ammonium chloride, which is a solid. That is the white dense film that you were talking about in secondary school days. You say when you open the gas jar of ammonia solution, you open the gas jar, or you open the jar of ammonium solution, aqueous ammonia, you open the jar of hydrochloric acid and you place them side by side. The hydrochloric acid gas that escapes from the HCl solution and the ammonia gas that escapes from the aqueous ammonia, they condense. They come together and they react and they condense to form the white dense film of ammonium chloride. That white dense film you see on top of the bottles, in between the bottles, it's a salt, and that is ammonium chloride salt. So that is why we take this also as a kind of acid-base reaction. But this is not limited to solution. There is no water here at all. There is no solution here. So this is another example of acid-base reaction. And the acid, what it does here, it releases a proton, even in the gas phase, to ammonia gas. So it releases proton to that ammonia. And then we have the ammonium chloride formed. Well, let me guess that you understand this a bit, but that one is an assumption. This is now what I want you to do for me in the chat section. In the chat section, pick the definition of, just pick definition of Bronsted-Lowry for an acid. Pick the definition of, pick the Arrhenius definition of an acid and compare the two. Type it in the chat section. What is the difference between Arrhenius definition of an acid and Bronsted-Lowry definition of an acid? Put it now in the chat section. Type it in the chat section. Okay. So type it there. I want to see the definition. Okay. All right. Arrhenius isn't constricted to solution. Well, this is not fully right. It is Bronsted-Lowry is not constricted to solution, not Arrhenius. Arrhenius acid must be in solution. Okay. Arrhenius acid involves aqueous solution. Okay, that's correct. While Bronsted-Lowry does not. Well, Arrhenius acid can also be in solution, and it may not be in solution. So Bronsted-Lowry acid can be in solution or may not be in solution. So Bronsted-Lowry theory is broader than Arrhenius theory of an acid. Arrhenius theory of an acid is restricted to solution, but a Bronsted-Lowry definition covers both solution and out of solution. Okay, I'm seeing different definitions, different differences. Okay, Arrhenius definition is limited. Okay. The thing is moving fast. I may not be able to read everything. All right, just put it there. Just type it there. Type it there. Okay. Yes, you're all doing very well. You're doing very well. Okay, let's take one or two questions more. Then I will show you the assignment we have against the next class. Ogunjomi Ajoke. Is Ogunjomi there?
Yes, sir. Good morning, sir.
Good morning.
Yes, sir. Sir, what is the difference between hydrogen chloride and hydrochloric acid? Is there a
Oh,
difference, sir?
okay. Did you just join the class? Or did you start with
Yes,
us
sir.
from the beginning?
Did not
Oh,
start from the beginning.
oh, you didn't start from the beginning. I've already given your friends that as classwork to give me the difference between hydrogen chloride and hydrochloric acid. So let me give you also that classwork. So try and find out and put in the chat section. What do you think is the difference between hydrogen chloride and hydrochloric acid? Since I've already given your friends your classmates as classwork in today's class, so you can also try and find out and put the answer. I'll be expecting your answer in the chat section. That's Bunyomi. Yes, I will be expecting your comments, your response in the chat section. Okay.
Okay, sir.
All right. Yeah, well done. Okay, let's take one more question. Just one more. Shimilore Adebayo.
Good morning, sir.
All right, good morning.
Yes, sir. My question is when ethanoic acid, I mean CH3COH,
Okay.
yes, and a weak acid from Vanja. Hello, sir.
Oh, I'm listening. Yes, I'm hearing you. I'm listening.
When it ionizes to hydrogen ion,
You and this ion. It's not ion, it's ion.
hydrogen ion, and CH3CO minus.
Okay.
Yes. So what's that reaction?
When ethanoic
CH3,
acid gives the ethanoate ion and also hydrogen ion in solution, right?
yes,
Okay, what's the name of that reaction?
yes,
Okay, all right. So that's a kind of ionization. You put ethanoic acid, you put that ethanoic, you dissolve it in the water, then you have the ethanoate ion and you also have the hydrogen ion in solution. So that is a kind of ionization. That is, you have pulled apart the anion, which is the ethanoate ion, from the cation, which is the hydrogen ion. So that is what you have just done. So it may not be fully ionized in solution. We'll look more into weak acids. We'll also look at strong acids in subsequent classes. We'll look at them. Okay. Did I answer your question? What is that? Okay. Let me assume I've answered your question. Okay, did I say I will take one more? That was the last one. Okay, I guess that's the last one. Okay, so that's the last question we are taking for today. Let me just share with you what you'll be having as your second assignment. As a second assignment, okay? And you'll be submitting that one on the same day with the previous assignment. Okay, let me just share the screen with you. The next couple of... All right, let me assume you can see the assignments right there. Let me assume you can see the assignment. Okay, this is assignment 1. Okay, yes, this is the second assignment. So under the second assignment, you will find out by yourself, you read. You differentiate between Arrhenius acid and Lewis acid. You know, we are focused more on Arrhenius acid and Bronsted-Lowry acid. But under this assignment, I want you to also differentiate between Arrhenius acid and Lewis acid and give 4 examples of Lewis acid. You submit it on the same day with assignment number 1. You can submit it today if you have the answer, it's fine. But ensure that you submit it just before the end of that March 28th day. Well, let's believe that we've been able to have a very good class today. And thank you all for your participation. Thank you all for your participation. And let me be wishing you a very great day ahead. Thank you for joining this class. We are very hopeful that we will see also physically, as God will give us the grace, when you come around physically to the University of Ibadan. So once again, you are welcome to the university. Do have a very great and blessed day.